I've been thinking a lot about patterns lately, the kind of patterns you see everywhere once you start looking for them. The spiral of a seashell, the branching of a tree, the way snowflakes form, the orbits of planets, the rhythm of your heartbeat. And what strikes me, what really stops me in my tracks when I think about it, is that underneath all of these things, underneath everything we can touch and see and measure, there's mathematics. Not just as a tool we use to describe things, but as something deeper, something more fundamental. It's like the universe is written in a language, and that language is mathematics. And the more we learn to read it, the more we realize that this isn't just a metaphor or a convenient way of talking about things. It's actually true in a way that's both beautiful and deeply mysterious. You see, when you look at a nautilus shell, you're seeing a spiral that follows a very specific mathematical pattern, a logarithmic spiral that can be described with precise equations. And it's not just one shell, it's every nautilus shell following the same mathematical rule. Galaxies do this too, spiral galaxies spinning through space, following the same kind of mathematical curve. And you might think, okay, that's interesting, these things look similar. But when you dig deeper, you find that it's not just similarity, it's the same mathematics, the same underlying structure governing things that exist on scales so vastly different that it seems almost impossible. A spiral galaxy is, hundreds of thousands of light years across, and a nautilus shell fits in your hand, and yet they're both expressing the same mathematical truth. How can that be? Why should the same patterns appear at every scale of existence, from the subatomic to the cosmic? And that's just the beginning, right? Because once you start noticing these patterns, you can't stop seeing them. The Fibonacci sequence, where each number is the sum of the two before it, 1, 1, 2, 3, 5, 8, 13, 21, and on, this sequence shows up in the arrangement of seeds in a sunflower, in the branching of trees, in the structure of pine cones, in the spirals of hurricanes. It's everywhere. And the ratio between consecutive Fibonacci numbers approaches something called the golden ratio, phi, approximately 1.618. And this number, this specific proportion, appears in art, in architecture, in the proportions of the human body, in the structure of DNA molecules, in the pattern of stock market fluctuations. It's as if nature has a preferred proportion, a mathematical aesthetic that it returns to again and again across completely different domains of reality. But here's where it gets really interesting, because these patterns aren't just pretty coincidences, they're actually the most efficient solutions to certain problems. The spiral of a shell allows the creature inside to grow without changing shape, maintaining structural integrity while increasing in size. The branching patterns of trees and river systems maximize the distribution of resources, nutrients or water, with minimal energy expenditure. The hexagonal structure of a honeycomb uses the least amount of wax to create the maximum amount of storage space. Nature, it seems, is solving optimization problems, and the solutions it arrives at are mathematical. And that raises this profound question, this question that's been bothering philosophers and physicists for centuries. Is mathematics something we invented to describe nature, or is it something we discovered that was already there, built into the fabric of reality itself? I mean, think about it this way. When Isaac Newton developed calculus, he wasn't just creating a useful tool for doing physics, though it certainly is that. He was uncovering a mathematical structure that describes how things change, how motion works, how the universe evolves over time. And the thing is, calculus works. It works so precisely, so accurately, that we can use it to predict the motion of planets centuries into the future, to calculate the trajectory of a spacecraft so it arrives at Mars at exactly the right moment, to design bridges and buildings that stand up to forces we can compute with extraordinary precision. The mathematics tells us what will happen, and then what will happen happens. That's astonishing when you really think about it. We scribble some symbols on paper, manipulate them according to certain rules, and somehow these manipulations tell us true things about the physical world. The physicist Eugene Wigner wrote this famous essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, and that title captures something essential about this mystery. Why should mathematics be so unreasonably effective? Why should abstract concepts, things that exist purely in our minds, things we can reason about without ever looking at the physical world, why should these correspond so perfectly to the way the universe actually works? There's no obvious reason why this should be true. We could imagine a universe where mathematics was just a useful approximation, where it worked okay sometimes but failed in other situations, where the patterns we see were rough and fuzzy rather than precise. But that's not the universe we live in. The universe we live in speaks mathematics with what seems like perfect fluency. And it's not just simple mathematics either, right? It's not just counting and basic geometry. The deeper we look into the nature of reality, the more sophisticated the mathematics becomes. Quantum mechanics, which describes the behavior of particles at the smallest scales, requires complex numbers that involve the square root of -1, which doesn't correspond to any quantity you can measure directly in the physical world. And yet these imaginary numbers, as they're called, are absolutely essential for describing quantum reality. Without them, the equations don't work, the predictions fail. The universe, at its most fundamental level, seems to operate according to rules that involve mathematical concepts that have no direct physical interpretation, and yet they're necessary, they're unavoidable if you want to understand what's actually happening. Or take symmetry, which is a mathematical concept, a way of describing things that remain unchanged under certain transformations. If you rotate a circle, it looks the same. That's rotational symmetry. If you reflect a square across its diagonal, you get the same shape. That's reflection symmetry. These are geometric ideas, mathematical abstractions. But it turns out that symmetries are fundamental to the laws of physics. Every conservation law in physics, every principle that says something is preserved, like energy or momentum or electric charge, every single one of them, these corresponds to a symmetry in nature. This is called Noether's theorem, after Emmy Noether, one of the greatest mathematicians who ever lived. And what it says is that conservation laws aren't separate from symmetries, they're the same thing expressed in different ways. The fact that energy is conserved, that the total energy in a closed system never changes. This comes from the fact that the laws of physics don't change over time. They're symmetric with respect to time translation. The fact that momentum is conserved comes from the fact that the laws of physics are the same everywhere in space, space translation symmetry. So symmetry, this abstract mathematical concept, isn't just a description we impose on nature. It's actually generative. It produces the fundamental conservation laws that govern all physical processes. And that's remarkable. It means that the architecture of reality, the deep structure underlying everything that happens, is mathematical in its essence, not just in our description of it. The universe couldn't conserve energy without having this mathematical symmetry built into its foundations. And that makes you wonder, what is the relationship between the mathematics and the physics? Is the mathematics causing the physics? Is the physical world actually made of mathematics in some sense? Or is there something else, something deeper that gives rise to both? Let me tell you about something that happened in the 19th century that really drives this point home. James Clerk Maxwell was studying electricity and magnetism, which at the time were thought to be two separate phenomena. Through a series of experiments and theoretical work by various scientists, it became clear that electricity and magnetism were related, that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Maxwell took all the known laws about electricity and magnetism and wrote them down as a set of equations, 4 equations that completely describe all electromagnetic phenomena. And when he looked at these equations, when he analyzed their mathematical structure, he found something that nobody expected. The equations predicted that electromagnetic disturbances should propagate through space as waves, traveling at a specific speed that could be calculated from the equations. And when Maxwell did the calculation, when he plugged in the known values for the electric and magnetic constants, he got a number that was very close to the known speed of light. Not close by coincidence, but exactly the same within the experimental uncertainty of the measurements at the time. And Maxwell realized he had this incredible insight that light itself must be an electromagnetic wave. The equations told him this. The mathematics revealed something about the nature of light that hadn't been put into the equations explicitly. Nobody had said, let's write down equations that explain light. They were just trying to describe electricity and magnetism, and out came light as a consequence of the mathematical structure. And then the equations predicted something else. They predicted that electromagnetic waves could exist at any frequency, not just at the frequency of visible light. And this led to the discovery of radio waves, microwaves, X-rays, gamma rays, the entire electromagnetic spectrum. All of this was hidden in the mathematics, waiting to be discovered. And it was discovered not by doing new experiments first, but by exploring the implications of the equations, by following where the mathematics led. That's happened again and again in the history of physics. Paul Dirac was trying to write down an equation that described electrons in a way that was consistent with both quantum mechanics and special relativity, and when he finally found the right equation, the Dirac equation, it had a surprising feature. For every solution describing an electron, there was another solution with opposite properties, opposite charge. Dirac puzzled over this for a while, trying to figure out if these negative energy solutions were just mathematical artifacts, mistakes in the equation, or if they meant something physical. And eventually he made this bold prediction. The equation is telling us that for every particle, there should be a corresponding antiparticle, identical in mass, but opposite in charge. A few years later, the positron, the antiparticle of the electron, was discovered in cosmic ray experiments, exactly as Dirac's equation had predicted. The mathematics had revealed something about the structure of reality that nobody had suspected, and then reality confirmed what the mathematics had said. You see this pattern over and over. General relativity, Einstein's theory of gravity, is fundamentally a mathematical theory about the geometry of space-time. Einstein realized that gravity isn't a force in the traditional sense, but rather a consequence of the curvature of space-time caused by mass and energy. He wrote down equations, the Einstein field equations, that describe how matter and energy curve space-time and how this curvature affects the motion of objects and the propagation of light. And these equations predicted all sorts of strange phenomena. They predicted that time runs slower in strong gravitational fields, that massive objects can bend the path of light, that the universe itself must be either expanding or contracting. It can't be static. They predicted black holes, regions of space-time where the curvature becomes so extreme that nothing, not even light, can escape. They predicted gravitational waves, ripples in the fabric of space-time itself that propagate at the speed of light. And every single one of these predictions has been confirmed by experiment and observation. Time dilation has been measured with atomic clocks. The bending of light by massive objects was first observed during a solar eclipse in 1919, confirming Einstein's theory. The expansion of the universe was discovered by Edwin Hubble. Black holes, once thought to be purely theoretical curiosities, are now known to exist in abundance throughout the universe. And in 2015, almost exactly a century after Einstein wrote down his equations, gravitational waves were directly detected for the first time by the LIGO experiment, when two black holes collided and merged more than 1 billion light years away. So the mathematics isn't just describing what we see, it's predicting things we haven't seen yet, things that seem bizarre and impossible, and then those things turn out to be real. The universe is more mathematical than we are, in a sense. The equations know things we don't know. They reveal aspects of reality that our intuition, our everyday experience, could never have guessed. And that's what makes this so profound, so mysterious. Because if mathematics were just a language we invented to describe nature, you'd expect it to be good at summarizing what we already observe, but not necessarily good at predicting radically new phenomena. But mathematics does exactly that. It tells us about aspects of reality we haven't encountered yet. And it's right. It's right far more often than you'd expect by chance. Now let's think about constants, these special numbers that appear throughout physics. There's pi, the ratio of a circle's circumference to its diameter, approximately 3.14159. This number shows up everywhere, not just in geometry, but in probability theory, in quantum mechanics, in the equations for waves and oscillations. Then there's e, the base of natural logarithms, approximately 2.71828, which appears in anything involving growth or decay, exponential processes, compound interest, radioactive decay, population dynamics. And then there are the fundamental constants of physics, the speed of light, c, approximately 300,000 kilometers per second, the gravitational constant, g, which determines the strength of gravitational attraction, Planck's constant, h, which sets the scale of quantum effects, the fine structure constant, which describes the strength of electromagnetic interactions. These numbers aren't arbitrary. They define the structure of our universe. If they were different, even slightly different, the universe would be fundamentally different. Stars might not be able to form, atoms might not be stable, chemistry might not be possible, life almost certainly wouldn't exist. And here's the thing about these constants. We don't know why they have the values they do. We can measure them with extraordinary precision, but we can't derive them from anything more fundamental. They seem to be, well, just given properties of the universe that could have been different, but happen to be what they are. Some physicists and cosmologists speculate that maybe these constants aren't actually constant across different universes, that we live in a multiverse where different regions have different values for these fundamental numbers, and we happen to be in a region where the constants allow for complexity and life, because obviously we couldn't be in a region where life is impossible. But that's speculative, and it raises its own questions. The point is, these mathematical values, these specific numbers, determine the character of physical reality, and we don't know if there's a deeper mathematical reason why they have to be what they are, or if they're just contingent facts about our particular universe. But let's go deeper, right? Let's talk about what mathematics actually is at its core. When you strip away all the applications, all the physics and engineering, what you're left with is a system of logical relationships, patterns of reasoning, structures of thought. Mathematics is about taking certain basic assumptions, axioms, and deriving conclusions from them through logical deduction. You start with things like, two things equal to the same thing are equal to each other, basic logical principles, and you build up from there, constructing elaborate structures of theorems and proofs, creating entire mathematical worlds that exist purely through logical necessity. And here's what's so strange. These purely abstract structures, these things that exist only in the realm of thought, turn out to describe the physical world. Take non-Euclidean geometry, for example. For thousands of years, geometry meant Euclidean geometry, the geometry of flat spaces where parallel lines never meet, where the angles of a triangle add up to 180 degrees. But in the 19th century, mathematicians started wondering, what if you changed some of the basic assumptions? What if you didn't assume that parallel lines never meet? And they discovered that you could create consistent logical geometries where space is curved, where the rules are different. These weren't just mistakes or curiosities, they were fully coherent mathematical systems, just as valid logically as Euclidean geometry, but describing different kinds of spaces. At the time, this was pure mathematics, abstract exploration with no connection to the physical world. And then Einstein came along with general relativity and showed that the actual geometry of space-time is non-Euclidean, that space is curved by mass and energy, and the mathematics needed to describe this curvature was exactly the non-Euclidean geometry that mathematicians had developed decades earlier for completely abstract reasons. This happens all the time in mathematics. Mathematicians explore abstract structures because they're interesting, because they're elegant, because they're there to be explored with no thought of practical application. And then decades or centuries later, physicists discover that these abstract structures describe something in the physical world. Complex numbers were studied for centuries before quantum mechanics needed them. Group theory, the study of symmetry and transformation, was developed as pure mathematics and later became essential for particle physics. Riemannian geometry, the mathematics of curved spaces, was created as an abstract generalization of geometry and later became the language of general relativity. It's as if the universe is exploring the same mathematical structures that mathematicians explore, or maybe it's that mathematicians, by exploring mathematics, are actually exploring the structure of possible realities. And our universe happens to be one of those possibilities that mathematics allows. And that brings us to this really deep question, this question that goes back to Plato and even earlier. Do mathematical objects exist? Not as physical things, obviously, but as real entities in some Platonic realm of abstract forms. When a mathematician proves that there are infinitely many prime numbers, is she discovering a fact that was already true? True even before humans existed? True even if the physical universe didn't exist? Or is she inventing a concept, creating something through human thought and language? Most mathematicians, if you ask them, will tell you that it feels like discovery, not invention. When you're working on a mathematical problem, it doesn't feel like you're making arbitrary choices. It feels like you're uncovering truths that were already there, hidden, waiting to be found. There's resistance, the way there would be if you were exploring a real landscape. Some paths lead somewhere, others dead end. Solutions, when you find them, have a sense of inevitability, of rightness, that doesn't feel like something you could have just made up differently. But then, if mathematical objects are real, in some sense, if numbers and shapes and functions exist independently of the physical world, independently even of minds to think about them, where are they? In what sense do they exist? They're not in space or time, they don't have mass or energy, they can't be detected by any physical instrument. And yet we can reason about them, discover truths about them, and these truths constrain what we can do. They're not arbitrary. You can't prove that 2 + 2 = 5, no matter how hard you try, no matter what axioms you start with, as long as you're talking about the standard natural numbers. That's a mathematical fact, and it's a fact in a way that seems stronger, more necessary than physical facts. Physical laws could have been different, we think, but mathematical truths, those seem necessary in a deeper way. Or are they? Kurt Gödel, one of the greatest logicians of the 20th century, proved something shocking about mathematics itself. He showed that in any sufficiently complex mathematical system, there are statements that are true but unprovable within that system. You can have a mathematical statement that's neither provable nor disprovable using the axioms and rules of the system, even though the statement is, in some intuitive sense, true. This is Gödel's incompleteness theorem, and it revealed fundamental limits to what mathematics can do. It means that mathematics can't be completely formalized, can't be reduced to a purely mechanical process of deriving theorems from axioms. There's always going to be this gap, these truths that slip through the net of formal proof. And this raises the question, if mathematical truth goes beyond what can be proved, what is the basis of mathematical truth? How do we know what's true in mathematics if not through proof? And there's something else Gödel showed, which is maybe even more disturbing. He proved that if a mathematical system is consistent, if it never leads to contradictions, then it can't prove its own consistency. You can't use mathematics to prove that mathematics is free from contradictions. You have to take that on faith or justify it using some system outside of mathematics, which raises the same problem again. So at the very foundation of mathematics, at the base of this edifice that seems so solid and certain, there's this unavoidable uncertainty, this incompleteness. Mathematics can't fully justify itself, can't pull itself up by its own bootstraps. It rests on assumptions that can't be proven, only believed. But here's the thing, right? Despite these philosophical puzzles, despite these fundamental limitations, mathematics works. It works in practice, it works for physics, it works for engineering, it works for predicting the behavior of physical systems with extraordinary accuracy. And that effectiveness, that unreasonable effectiveness, suggests that whatever mathematics is, however we should think about its ontological status, it's tapping into something real about the structure of the universe. Maybe the universe is mathematical in some deep sense. Maybe mathematical structures are the only things that exist, and what we call the physical world is actually a particular mathematical structure, one that has the property of being able to contain observers who can think about mathematics. That's the view of some physicists and philosophers, this idea that reality is mathematics, that the physical and the mathematical aren't two different things, but the same thing seen from different perspectives. Think about information for a moment. Information theory, developed by Claude Shannon in the 1940s, treats information as a mathematical quantity that can be measured and manipulated. A bit is the fundamental unit of information, a binary choice, yes or no, 1 or 0. And it turns out that you can think about physical systems in terms of information. The state of a particle can be described by the information needed to specify its position and momentum. The entropy of a system, which in thermodynamics is a measure of disorder, can be understood as a measure of information, specifically the information you don't have about the microscopic state of the system. And in quantum mechanics, information becomes even more fundamental. The state of a quantum system is information, and the evolution of that system over time is the processing of that information according to the rules of quantum mechanics. Some physicists, like John Wheeler, have suggested that information is the most basic constituent of reality, that it from bit, as Wheeler put it, that the physical universe emerges from information in some fundamental way. And if that's true, if information is fundamental, then maybe the reason mathematics describes reality so well is that mathematics is the science of information, of patterns, of structure, and reality is made of structure. The universe isn't made of stuff, fundamentally. It's made of patterns, relationships, information, and mathematics is the language of patterns and relationships. That would explain why mathematics is so effective, because it's not just describing the universe from the outside, it's the same kind of thing as the universe. Both are structures of information, patterns of relationship, and the reason we can discover truths about the physical world by doing pure mathematics is that we're exploring the space of possible patterns. And the physical world is one instantiation of those patterns, one way that patterns can arrange themselves to create something that persists, something that has causal structure, something that can be experienced. But let's not get too far ahead of ourselves. Let's come back to something more concrete, something we can actually observe and measure. Let's talk about chaos theory and fractals, because these reveal another aspect of how mathematics structures reality. Chaos theory is the study of systems that are deterministic, meaning they follow precise mathematical laws but are unpredictable in practice because they're extremely sensitive to initial conditions. The classic example is weather, which is why it's so hard to make accurate weather forecasts more than a few days in advance. The atmosphere follows the laws of physics, the equations of fluid dynamics, but tiny differences in the initial state of the atmosphere, differences too small to measure, get amplified over time until they completely change the outcome. A butterfly flapping its wings in Brazil could in principle lead to a tornado in Texas, not because the butterfly caused the tornado directly, but because the atmosphere is a chaotic system where small perturbations can have large effects. Edward Lorenz discovered this in the 1960s when he was running computer simulations of weather patterns. He ran the same simulation twice with initial conditions that differed only in the 6th decimal place, and he expected to get essentially the same results, but instead the two simulations diverged completely, giving totally different weather patterns. And Lorenz realized that this sensitivity to initial conditions is a fundamental property of certain kinds of systems, not a flaw in the simulation, but a reflection of how these systems actually work. And when you visualize the behavior of chaotic systems, when you plot their evolution over time in what's called phase space, you get these beautiful, intricate structures called strange attractors. The Lorenz attractor, for example, looks like two butterfly wings, and the trajectory of the system traces out this pattern, looping around one wing and then the other in a way that never exactly repeats, but always stays within this specific shape. And these shapes, these attractors, are fractals, patterns that have structure at every scale, where if you zoom in on a small part of the pattern, you see the same kind of complexity as in the whole thing. Fractals are everywhere in nature, in coastlines and mountain ranges, in the branching of blood vessels and the structure of lungs, in clouds and turbulent flows, in the distribution of galaxies across the universe. And fractals have this remarkable property. They have fractional dimension. A line is one-dimensional, a plane is two-dimensional, but a fractal curve can have a dimension between 1 and 2, like 1.5 or 1.7, because it's so crinkly and convoluted that it's more than a line but less than a plane. It fills space in a way that's intermediate between dimensions. And this isn't just a mathematical curiosity, it's a property of real physical structures. A crumpled ball of paper has a fractal structure, and its dimension tells you something about how efficiently it fills space. The coastline of Britain has a fractal structure, and its effective length depends on the resolution at which you measure it, getting longer and longer as you include more and more detail. So here's what's remarkable about this. Simple mathematical rules can generate infinite complexity. The Mandelbrot set, one of the most famous fractals, is defined by an incredibly simple equation. Z becomes z squared plus c, where z and c are complex numbers, and you iterate this equation and see whether the values stay bounded or diverge to infinity. That's it, that's the whole definition. But when you visualize which values of c stay bounded and which diverge, you get this infinitely complex, endlessly beautiful pattern with tendrils and spirals and shapes within shapes, and the boundary of the set is fractal, with structure at every scale, no matter how far you zoom in. You can explore the Mandelbrot set forever and keep finding new patterns, and all of this complexity emerges from a simple mathematical rule. And that tells us something profound about how complexity arises in nature. You don't need complicated laws to get complicated behavior. You can get incredible richness, infinite variety, from simple rules that are iterated again and again. That's what happens in evolution: simple rules, mutation and selection, iterated over millions of generations, producing all the diversity of life on Earth. That's what happens in the growth of a snowflake: simple rules about how water molecules attach to ice, iterated billions of times, producing these intricate six-fold symmetric patterns that are all different from each other, but all recognizably snowflakes. And this is another way that mathematics illuminates the structure of reality. It shows us that complexity doesn't require complexity at its foundation. The universe can be built on simple mathematical principles and still generate everything we see, all the richness and diversity and apparent chaos, because iteration of simple rules can produce unlimited complexity. And that's beautiful, isn't it? There's an elegance to that, a parsimony that suggests maybe the universe really is mathematical at its core, because mathematics is the realm where you can have both simplicity and complexity, where a few basic principles can unfold into infinite richness. Let's talk about quantum mechanics again, because this is where the mathematics gets really strange, really counterintuitive, and yet it's absolutely essential for understanding the microscopic world. In classical physics, you can know exactly where a particle is and how fast it's moving. And if you know that, you can predict with certainty where it will be in the future. But in quantum mechanics, that's not how it works. A particle doesn't have a definite position and momentum at the same time. It has a wave function, which is a mathematical object that tells you the probability of finding the particle at different locations if you measure its position. The wave function evolves according to a mathematical equation, the Schrödinger equation, which is deterministic, meaning if you know the wave function now, you can calculate what it will be at any future time. But when you actually make a measurement, when you look to see where the particle is, the wave function collapses, and you get one specific outcome, chosen randomly according to the probabilities encoded in the wave function. And before you measure, the particle isn't anywhere definite, it's in a superposition of all possible positions, existing in a mathematical state that doesn't correspond to any single classical property. This is deeply weird, right? It means that the fundamental description of a quantum system is probabilistic, not deterministic. It means that a particle can be in multiple states at once, in a very real mathematical sense, and only chooses a definite state when measured. And it means that the act of measurement itself plays a fundamental role in determining physical reality. This isn't just about our ignorance, about not knowing which state the particle is in. It's that the particle genuinely isn't in any single state until it's measured. The mathematics forces this conclusion on us. If you try to interpret quantum mechanics as a theory of particles that have definite properties that we just don't know, you run into contradictions with experiment. Bell's theorem, proved in the 1960s and tested experimentally many times since, shows that quantum mechanics is incompatible with any theory where particles have definite properties independent of measurement and where influences are limited to the speed of light. Something has to give, and what gives is our classical intuition about how reality works. So the mathematics of quantum mechanics is telling us something very strange about the nature of reality. It's telling us that the physical world at its most fundamental level is probabilistic, indeterminate, non-local, with parts that are entangled in ways that defy our ordinary notions of separateness and locality. Two particles can be entangled such that measuring one instantly affects the other, no matter how far apart they are, not because some signal travels between them faster than light, but because they're part of a single quantum system that can't be factored into separate parts. The mathematics describes this perfectly, predicts the correlations we observe with extraordinary accuracy, but the interpretation, what it means for our understanding of reality, that's still being debated almost a century after the theory was developed. And that's partly because the mathematics itself is so abstract, so far removed from everyday experience, that translating it into ordinary language, into a picture we can visualize, seems almost impossible. We're forced to use the mathematics itself as our primary description of reality, and to accept that maybe reality at this level just is mathematical, is a state in an abstract mathematical space that we call Hilbert space, and physical properties are operations on that state, and outcomes of measurements are eigenvalues of those operations. And if none of that makes intuitive sense, well, maybe that's because intuition is a guide to the macroscopic world of everyday experience, not to the quantum realm where our everyday concepts don't apply. And yet, quantum mechanics works. It's the most successful theory in the history of science in terms of predictive accuracy. The calculations agree with experiments to better than 1 part in a billion. All of modern electronics depends on quantum mechanics, transistors and semiconductors and lasers and LEDs. None of these would work if quantum mechanics weren't correct. Chemistry is fundamentally quantum mechanics, the behavior of atoms and molecules, the bonds between them, the reactions they undergo. All of this can be calculated from quantum principles. And we've started building quantum computers, which exploit quantum superposition and entanglement to perform certain calculations exponentially faster than classical computers. So the mathematics of quantum mechanics isn't just an abstract description. It's a tool for manipulating reality, for building technologies that depend on quantum effects. And that's another piece of evidence that the mathematics is fundamental, not just a human invention, because we can use the mathematical structure to predict and control physical phenomena in ways that work reliably and precisely. Now let's think about infinity, because infinity is a purely mathematical concept, something that doesn't exist in the physical world in any direct sense. And yet it's essential for understanding the physical world. Calculus, which is the foundation of physics, is built on the concept of limits, of considering what happens as quantities approach infinity or as intervals become infinitesimally small. When you calculate the velocity of an object, you're finding the limit of average velocity as the time interval approaches 0. When you calculate the area under a curve, you're summing an infinite number of infinitesimal strips. These are mathematical procedures involving infinity, and they give finite, well-defined results that match what we measure in the physical world. But what does it mean that the mathematics involves infinity? Is infinity real? Can anything physical actually be infinite? The universe might be infinite in extent, stretching on forever in all directions, or it might be finite but unbounded, like the surface of a sphere, which is finite in area but has no edge. We don't know which is the case, and current observations don't tell us definitively. But even if the universe is finite in extent, space and time are continuous in the sense that you can subdivide them indefinitely, at least according to our current theories. Between any 2 points in space, there are infinitely many other points. Between any 2 moments in time, there are infinitely many other moments. That's what it means for space and time to be continuous, to be described by real numbers rather than discrete values. And if that's true, if space and time are really continuous, then there are infinitely many points in any finite region of space, infinitely many moments in any finite interval of time. Infinity is woven into the structure of the physical world at a fundamental level. But then there are problems, mathematical problems, that show up when you take infinity too seriously in physics, when you try to calculate certain quantities in quantum field theory, like the energy of empty space. You get infinite results, which doesn't make physical sense. These infinities have to be removed through a mathematical procedure called renormalization, which is well established and works in practice. But it's always felt a bit unsatisfying, like we're sweeping something under the rug. And some physicists think that the appearance of infinities in our theories is a sign that the theories are incomplete, that at some fundamental level, space and time might not be continuous after all, might be made of discrete chunks, quanta of space and time, so that if you zoom in far enough, you reach a smallest possible distance, the Planck length, and a smallest possible time, the Planck time. And there's no infinity because there's no infinite divisibility. Space and time would be like a digital photograph which looks continuous from a distance, but is actually made of discrete pixels if you zoom in close enough. But even if space and time are discrete at the Planck scale, the mathematics we use to describe them is continuous, involves real numbers and calculus, and it works extraordinarily well at all scales we can currently probe. So in some sense, infinity is an essential part of the mathematical structure we use to understand reality, even if it's not clear whether infinity is a feature of reality itself or just a feature of our description of reality. And that distinction between the map and the territory, between our mathematical models and the physical reality they describe, that's always there, always creating this tension. Are we describing reality as it is, or are we creating mathematical models that approximate reality well enough for our purposes? And if the latter, if mathematics is just a tool, why does it work so well? Why do the approximations turn out to be so precise? Why do purely mathematical explorations lead to predictions of new physical phenomena that are then discovered? Let me tell you about something called the holographic principle, because this is one of the most mind-bending ideas to come out of theoretical physics in recent decades, and it's deeply mathematical. Black holes, as I mentioned earlier, are regions of space-time where gravity is so strong that nothing can escape, not even light. And there's a mathematical result derived from general relativity that says black holes have entropy, a measure of information or disorder, and this entropy is proportional to the surface area of the black hole's event horizon, the boundary beyond which nothing can escape. Not proportional to the volume, which is what you'd expect for ordinary objects, but to the surface area. And that's strange because it suggests that all the information about what's inside the black hole, all the matter and energy that fell in, is somehow encoded on the two-dimensional surface of the event horizon. It's as if the three-dimensional interior is a hologram, a projection from the two-dimensional boundary. And then physicists started wondering, if this is true for black holes, maybe it's true more generally. Maybe our entire three-dimensional universe is actually a hologram, a projection from information encoded on a two-dimensional boundary at the edge of the universe. This is called the holographic principle, and it's supported by mathematical results in string theory and quantum gravity. It suggests that the number of degrees of freedom in any region of space, the amount of information that can be stored there, is limited not by the volume of the region, but by the area of its boundary. And if that's true, it means that our experience of living in three dimensions of space is, in some sense, an illusion, or at least not the most fundamental description. The fundamental reality might be two-dimensional, and three-dimensionality emerges from that. And this is all mathematical. It comes from analyzing the mathematics of quantum gravity, from pushing the equations to their logical conclusions. And the conclusions are bizarre, but they're mathematically consistent, and they solve certain puzzles about black holes and quantum mechanics. So here's the thing. The mathematics is leading us to conclusions about the nature of reality that are completely counterintuitive, that violate our everyday understanding of what space and dimensions are. And yet these conclusions follow from taking the mathematics seriously, from trusting that the equations are telling us something true. And maybe they are. Maybe the universe really is holographic in some sense. Or maybe we're pushing the mathematics beyond its domain of validity into regimes where our current theories break down and need to be replaced by something deeper. We don't know yet, but the fact that mathematics leads us to these ideas, that it opens up these possibilities, that's part of what makes it so powerful and so mysterious. Let's think about emergence, about how complex behavior arises from simple components. An individual neuron in your brain is a relatively simple cell. It receives signals from other neurons, integrates them, and if the combined signal exceeds a threshold, it fires, sending a signal to other neurons. That's basically it. That's what a neuron does. But you have about 86 billion neurons in your brain, and each neuron is connected to thousands of others, forming a network of staggering complexity. And from this network, from the pattern of firing and connectivity among billions of simple units, emerges consciousness, thought, memory, emotion, creativity, everything that makes you who you are. The mathematics of neural networks, the equations that describe how signals propagate and how connections strengthen or weaken based on experience, these can model aspects of brain function. can create artificial neural networks that learn to recognize patterns, to translate languages, to generate text and images. But we don't understand how subjective experience, how qualia, the feeling of what it's like to see red or taste coffee or feel pain, how that emerges from the physical processes in the brain. And maybe we can't understand it in terms of individual neurons and synapses. Maybe consciousness is an emergent property that exists at a higher level of description that requires a different kind of mathematics, a mathematics of information integration or of dynamical systems or something we haven't thought of yet. Emergence is when the whole is more than the sum of the parts, when new properties appear at higher levels of organization that couldn't be predicted, at least not easily, from knowing everything about the lower levels. Water molecules are made of hydrogen and oxygen atoms bound together. And if you know the properties of individual water molecules, you can, in principle, calculate the properties of liquid water, but it's incredibly difficult. And the liquid properties like fluidity and surface tension aren't obvious from looking at one molecule. They emerge from the collective behavior of trillions of molecules interacting. And there are levels of emergence stacked on top of each other. Atoms emerge from quantum fields, molecules emerge from atoms, cells emerge from molecules, organisms emerge from cells, ecosystems emerge from organisms, societies emerge from individuals. And at each level, new patterns appear, new regularities, new laws that are effective at that level, even though, in principle, everything reduces to the fundamental laws of physics. But the reductionist program, the idea that you can understand everything by understanding the fundamental particles and forces, that's only part of the story. You also need to understand how organization and pattern arise, how structures at one level become the components of structures at the next level. And that's a mathematical story, a story about complexity and information and dynamics. And this is where mathematics really shines, because mathematics is the science of pattern and structure. And emergence is all about patterns at different scales. The mathematics of fractals shows how patterns can repeat at every scale. The mathematics of cellular automata, simple systems where cells in a grid follow simple rules based on their neighbors, shows how complex global patterns can emerge from local interactions. Conway's game of life is a famous example. A cellular automaton with incredibly simple rules. A cell that's on stays on if it has 2 or 3 neighbors that are on, otherwise it turns off. And a cell that's off turns on if it has exactly 3 neighbors that are on. That's it. But from these simple rules, you can create patterns that move, that replicate, that build complex structures. It's Turing complete, meaning you can, in principle, build a computer inside the game of life, which itself is a pattern of cells following simple rules. And that emergence of complexity from simplicity, that's a mathematical phenomenon. And it's also, we think, how the universe works, how simple fundamental laws give rise to the incredible richness and diversity of the world we experience. There's also something called emergence in physics that's related but distinct. In many particle systems, new phenomena can appear that don't exist for individual particles. Superconductivity is an example, where certain materials, when cooled below a critical temperature, can conduct electricity with zero resistance. This isn't a property of individual electrons. It's a collective phenomenon that emerges when electrons form pairs and move through the material in a coordinated way. And the mathematics that describes superconductivity is very different from the mathematics of individual electrons. It's a mathematics of phase transitions and order parameters and symmetry breaking. Or take phase transitions more generally, like water freezing into ice or magnetizing in a magnetic field. At the transition point, the system exhibits critical behavior, with correlations extending over long distances and fluctuations at all scales. And this is described by scaling laws and renormalization group theory, sophisticated mathematical frameworks that capture the universal properties of phase transitions, properties that are the same for completely different physical systems because they have the same mathematical structure. So mathematics gives us a way to see the commonality beneath surface diversity, to recognize that different physical systems can be governed by the same mathematical principles. And that's another piece of the puzzle of why mathematics is so effective, because the same mathematical structures appear in wildly different contexts. And if you understand the mathematics, you can transfer insights from one domain to another. The mathematics of waves, for instance, applies to water waves, sound waves, electromagnetic waves, quantum mechanical wave functions, seismic waves, even traffic jams and financial markets. The same equations, the same solutions, the same patterns of interference and diffraction and resonance. The mathematics is more general than any particular physical instantiation, and that generality is part of its power. Now, I want to talk about beauty, because mathematicians often talk about the beauty of mathematics, the elegance of a proof or an equation, and this isn't just a metaphor, it's a genuine aesthetic experience. Paul Dirac famously said that it's more important for an equation to be beautiful than for it to agree with experiment, because if it's beautiful, it's probably pointing toward a deep truth. And if it doesn't agree with experiment yet, maybe we're not measuring the right thing, or maybe the equation describes something we haven't discovered yet. And there's something to that, because the equations that have turned out to be most fundamental, most successful in describing nature are also almost universally described as beautiful by people who understand them. Maxwell's equations, Einstein's field equations, the Dirac equation, the Schrödinger equation, these are all considered beautiful. And part of what makes them beautiful is their simplicity, their symmetry, their inevitability. They feel like they couldn't have been otherwise, like they're true in a necessary way, not just contingently. And this sense of beauty isn't arbitrary, it's related to deep structural features that we value in mathematics: symmetry, simplicity, unity, generality. An equation that unifies seemingly disparate phenomena, that reveals a common structure underlying different things. That's beautiful. An equation that's symmetric, that looks the same under certain transformations, that's beautiful. An equation that's simple, that expresses something complex with minimal machinery, that's beautiful. And these aesthetic judgments aren't separate from mathematical truth, they're intertwined with it. Beautiful equations tend to be the ones that work, that survive experimental testing, that turn out to describe real features of the universe. And that's mysterious, isn't it? Why should the universe care about what we find beautiful? Why should our aesthetic sense, this subjective feeling of elegance and harmony, correlate with objective truth about physical reality? Maybe it's because evolution shaped our minds to recognize pattern and structure. And beauty is what we experience when we recognize deep patterns, fundamental structures that unify and explain. Or maybe it's that mathematics itself has an aesthetic dimension, that mathematical objects have properties that can be evaluated aesthetically, and the universe, being mathematical, naturally expresses those aesthetic properties. Or maybe truth and beauty are related in some fundamental way, that what's true at the deepest level tends towards simplicity and symmetry and elegance, not because of any principle we understand, but because that's the character of reality, and our sense of beauty is attuned to recognizing that character. Whatever the reason, the connection between mathematics and beauty is real, and mathematicians rely on it, use aesthetic judgments to guide their research, to evaluate conjectures, to decide which directions are worth pursuing. And often they're right. The beautiful conjecture turns out to be true. The elegant approach leads to a proof. The symmetric theory predicts phenomena that are then discovered. So beauty isn't just decoration, it's a feature of the mathematical structure of reality, or at least a reliable guide to it. And that adds another layer to the mystery of mathematics, because it suggests that the universe isn't just mathematical, it's mathematically beautiful, structured in ways that appeal to our sense of harmony and proportion and elegance. And those ways happen to be the ways that work, that are stable, that persist, that allow for complexity and life and minds that can contemplate the mathematics that underlies it all. Let's consider the role of mathematics in cosmology, in understanding the origin and evolution and ultimate fate of the universe. The Big Bang theory, our current best model of cosmic history, is fundamentally a mathematical theory. It starts with Einstein's field equations applied to the universe as a whole, assuming the universe is homogeneous and isotropic on large scales, the same in all directions and at all places when averaged over sufficiently large regions. From these assumptions and these equations, you derive a solution called the Friedmann-Lemaitre-Robertson-Walker metric, which describes an expanding universe. The mathematics predicts that the universe was smaller and denser in the past, and if you extrapolate backward, you reach a point about 13.8 billion years ago, when the density and temperature become infinite, a singularity, which is where the Big Bang model begins. Not an explosion in space, but the expansion of space itself, carrying galaxies apart like dots on an inflating balloon. And the mathematics makes specific predictions. It predicts that as the universe expanded and cooled, protons and neutrons formed, then atomic nuclei, then atoms, and the relative abundances of hydrogen, helium, and other light elements can be calculated from the physics of nuclear reactions in the early universe. And those predictions match the observed abundances extraordinarily well. The mathematics predicts that there should be a background of microwave radiation filling the universe, the afterglow of the Big Bang, and that radiation was discovered in 1964, and its temperature and properties match the predictions with stunning precision. The mathematics predicts that the universe should be flat or nearly flat on large scales, meaning the geometry of space should be Euclidean or very close to it. And observations of the cosmic microwave background and the large-scale structure of galaxies confirm this. So the mathematics of general relativity, applied to the universe as a whole, has given us a comprehensive history of the cosmos, from the first fractions of a second after the Big Bang to the present day, and eventually to the far future. And it's all mathematical. These aren't just qualitative stories, they're precise calculations that agree with observations. And the mathematics continues to push our understanding forward. It predicts that the very early universe underwent a period of exponential expansion called inflation, which would explain why the universe is so homogeneous and flat. And while inflation is still a hypothesis, not confirmed the way the Big Bang itself is, it's motivated by mathematics, by trying to solve certain puzzles that arise in the standard Big Bang model. The mathematics also tells us that most of the universe is made of things we can't see, can't directly detect. Dark matter, which doesn't emit or absorb light, is needed to explain the motion of galaxies and the formation of large-scale structure, and we infer its existence from its gravitational effects, which are predicted by the mathematics of general relativity and confirmed by observations. Dark energy, an even more mysterious component that seems to be causing the expansion of the universe to accelerate, is needed to explain the observed brightness and distance of distant supernovae, and it's described mathematically as a cosmological constant in Einstein's equations, or possibly as something more exotic, a field that varies in space and time. But in either case, it's the mathematics that reveals these components, that tells us the universe isn't just the matter we can see, the stars and galaxies and gas, but also these dark components that together make up about 95% of the total energy content of the universe. And the ultimate fate of the universe is also written in the mathematics. If dark energy remains constant, if it really is a cosmological constant, then the expansion of the universe will continue forever, accelerating, and the universe will grow ever colder and more dilute. Stars will burn out, black holes will evaporate through Hawking radiation, and eventually, in an unimaginably distant future, the universe will reach a state of maximum entropy, a heat death where no more structure can form, no more processes can occur, everything is spread out and uniform and dead. Or, if dark energy behaves differently, if it changes over time, the universe might end differently, might even collapse back on itself in a big crunch, though current observations suggest this is unlikely. The point is, the mathematics allows us to extrapolate forward and backward, to understand the history and destiny of the entire cosmos. And while there's still uncertainty, still unknowns, the framework is mathematical. And the answers will come from better mathematics, better observations, deeper understanding of the equations. And here's what's so striking about this. The equations that govern the smallest scales, quantum mechanics, and the equations that govern the largest scales, general relativity, these are both extraordinarily successful, both tested to high precision in their respective domains, but they're incompatible with each other. Quantum mechanics requires a fixed space-time background. It doesn't account for the curvature and dynamics of space-time itself. General relativity is a classical theory. It doesn't incorporate quantum effects, doesn't treat gravity as mediated by discrete quanta the way the other forces are. And at scales where both gravity and quantum effects are important, like the interior of black holes or the very earliest moments of the Big Bang, neither theory is adequate, and we don't have a consistent mathematical framework that unifies them. This is the problem of quantum gravity, one of the biggest unsolved problems in physics, and it's fundamentally a mathematical problem. We need new mathematics, a new mathematical structure that can describe space-time and matter in a way that's consistent with both quantum principles and general relativity. String theory is one attempt at this, a mathematical framework where the fundamental entities aren't point particles but one-dimensional strings, and the different vibrational modes of these strings correspond to different particles. In string theory, gravity emerges naturally. The graviton, the quantum of gravitational force, is one of the vibrational modes of the string, and the theory is mathematically consistent in ways that other attempts at quantum gravity are not. But string theory requires extra dimensions of space beyond the three we experience, typically 6 or 7 extra dimensions that are curled up so small we don't notice them, and it predicts a huge landscape of possible vacuum states, possible universes with different properties, which makes it hard to test, because almost any observation could be accommodated by choosing the right vacuum state. Loop quantum gravity is another approach, which keeps space-time fundamental but quantizes it, treats it as a network of discrete chunks rather than a smooth continuum, and this avoids some of the mathematical infinities that plague other quantum gravity theories. But loop quantum gravity has its own challenges, its own unresolved questions, and it's not yet clear how to recover general relativity in the limit where quantum effects become negligible. The point is, we don't yet have the final mathematical theory, the ultimate description of reality that unifies everything. We're still searching, still exploring different mathematical structures, trying to find one that works, that matches observation, that resolves the contradictions between our current best theories. And this search is guided by mathematics, by what's mathematically possible, what's mathematically consistent, what's mathematically beautiful. And there's confidence among physicists that the answer is out there, that there is a mathematical structure that describes quantum gravity, even if we haven't found it yet, because mathematics has always been reliable, has always turned out to be the right language for describing nature. And that confidence, that faith in mathematics, is based on centuries of success, on the repeated experience that mathematical exploration leads to physical insight, that the universe really does speak mathematics. But we should also be humble, right? Because there have been times when mathematical theories were beautiful, elegant, compelling, and wrong. Epicycles, the idea that planets move in circles on circles, was mathematically sophisticated and fit the observations reasonably well for centuries, but it was ultimately replaced by the elliptical orbits of Kepler and the gravitational theory of Newton. Newtonian mechanics itself seemed like the final word for 200 years, a complete mathematical description of motion and force, until it was superseded by relativity and quantum mechanics. So mathematics can mislead as well as illuminate, and we have to be careful not to confuse mathematical beauty with truth, not to assume that an elegant equation must be right just because it's elegant. But having said that, the track record is impressive. The theories that have replaced older theories have generally been more mathematical, not less, more abstract, more sophisticated, revealing deeper structures. So the trend is toward mathematics playing an ever more central role in our understanding of reality, and there's no sign that this trend is reversing. And let me bring this back to something personal, something human, because all of this mathematics, all of these equations and theorems and proofs, they're not just abstract intellectual games. They're part of how we make sense of our existence, how we understand our place in the universe. When you look up at the night sky and see stars and planets, you're seeing light that traveled across the cosmos, and the path of that light, the fact that you can see it, depends on the properties of space-time, on the electromagnetic spectrum, on quantum mechanics allowing atoms to emit and absorb photons. You're made of atoms forged in the cores of stars and scattered into space when those stars exploded, and the fusion reactions that created those atoms, the nucleosynthesis in stellar cores that's described by quantum mechanics and general relativity. The fact that you exist, that you can think and feel and wonder about mathematics, depends on the particular values of the fundamental constants, on the specific laws of physics that allow for chemistry and biology and complexity. So when we study mathematics, when we uncover the mathematical structures underlying reality, we're not just learning abstract facts, we're learning about ourselves, about where we came from, about the conditions that made our existence possible. And there's something profound about that, something that connects the most abstract, most theoretical aspects of mathematics to the most concrete, most personal aspects of human life. We're not outside observers looking at the universe from some detached vantage point. We're part of the universe, made of the same stuff, governed by the same laws, and our ability to understand those laws, to formulate them mathematically, to recognize the patterns, that ability is itself a product of the universe, a manifestation of the mathematical structure, becoming aware of itself. And maybe that's the deepest mystery of all, not just why mathematics describes reality, but why the universe contains structures capable of understanding mathematics, capable of doing science and proving theorems and asking why. There's no obvious reason why the universe should produce conscious minds, why matter should organize itself into brains that can contemplate the abstract structures that govern their own existence. But it did. We're here, and we can do mathematics. And we find that mathematics gives us genuine insight into the nature of reality. And that loop, that reflexivity, the universe producing minds that can understand the mathematics of the universe, that's perhaps the most remarkable fact of all, and it's not something we can explain, at least not yet. It's just the situation we find ourselves in, and it's astonishing. There's a concept in philosophy called the anthropic principle, which points out that any observations we make about the universe must be compatible with our existence as observers. Because if the universe didn't allow for observers, we wouldn't be here to observe it. And some people argue that this explains why the fundamental constants have the values they do, because if they were different, we wouldn't exist. So obviously we find ourselves in a universe where they have values consistent with life. But that doesn't really explain why the universe has these properties, it just explains why we observe them. It's like saying the reason you won the lottery is that you're the person who bought a winning ticket, which is true but doesn't explain why that ticket won. There might be deeper reasons, maybe a multiverse where different regions have different constants and we happen to be in a region where life is possible. Or maybe some principle we don't understand that determines the constants. Or maybe it's just chance and we're incredibly lucky. We don't know, and that's okay. Not knowing is part of the process, part of the journey of understanding. And I think that's important to remember, that for all the success of mathematics in describing reality, for all the equations and theories and predictions, there's still so much we don't understand. We don't know what dark matter is, what it's made of, even though we can calculate its gravitational effects. We don't know what dark energy is, why the expansion of the universe is accelerating. We don't know how to unify quantum mechanics and general relativity. We don't know whether the universe is finite or infinite, whether there are other universes, whether the laws of physics could have been different. We don't know how life began, how consciousness arises from matter, whether we're alone in the universe. We don't even know whether mathematics is complete, whether there are mathematical truths we can never prove, questions we can never answer. Gödel showed that there are limits to formal systems, and maybe there are limits to what we can know about the physical universe as well, not practical limits based on our current technology, but fundamental limits written into the structure of mathematics and logic. But that incompleteness, that uncertainty, it doesn't diminish the achievement of what we do understand. The fact that we can use mathematics to explain the motion of planets, the behavior of light, the evolution of the universe, the structure of atoms, the chemistry of life, that's extraordinary. The fact that patterns we discover through pure thought, through playing with symbols and logic, turn out to describe the real world, that's a miracle, in a sense. Though it's a miracle we've learned to rely on. And every time mathematics leads us to a new discovery, every time a prediction is confirmed, every time a technology works because the mathematics says it should, it reinforces this sense that mathematics is fundamental, that the universe really is mathematical in some deep sense, that the patterns we find in our minds are also the patterns that structure reality. And so we continue exploring, continue developing new mathematics, continue testing it against observation, continue being surprised when the mathematics knows things we don't, when it predicts the unexpected and turns out to be right. And maybe someday we'll understand why this works, why mathematics is so unreasonably effective, why the universe is comprehensible at all. Or maybe that question is beyond what we can answer. Maybe it's one of those fundamental mysteries that doesn't have a deeper explanation. It just is the way things are. But either way, the journey is worthwhile, the pursuit of understanding is meaningful because it connects us to something larger than ourselves, something that transcends our individual lives and our particular moment in history. It connects us to the deep structure of reality, to the mathematical patterns that existed before we discovered them and will continue to exist after we're gone. And there's beauty in that, a kind of eternal beauty that mathematics has, where truths once proven remain true forever, where the structure we uncover is something permanent, something that future civilizations, if they exist, will discover too, because they're exploring the same mathematical landscape that we're exploring, the same space of logical possibilities. The Pythagorean theorem is true whether humans exist or not, whether Earth exists or not, whether the universe exists or not, in some Platonic sense. And by discovering it, by proving it, we're participating in something that goes beyond the physical, beyond the temporal, something that's as close can be to eternity as anything we know. And that gives meaning to the enterprise of mathematics, of science, of trying to understand the world, because we're not just accumulating useful information, we're not just building technologies, though those are valuable too. We're uncovering truths about the fundamental nature of reality, and those truths are beautiful, and they're ours to discover. And the fact that we can discover them, that our minds are capable of grasping these abstract structures, that's perhaps the greatest wonder of all. So maybe the answer to why mathematics describes reality is that reality is mathematics, that the physical world is a mathematical structure, one particular structure among all possible mathematical structures, and what we call physical laws are just the properties of that structure, the way it's organized, the patterns it contains. And what we call existence, the fact that this structure is real rather than merely possible, maybe that's something we can't explain. Maybe existence itself is the deepest mystery, the one thing we can't derive from anything more fundamental. But we exist, and the universe exists, and it's mathematical, and we can understand it at least partially, and that understanding is one of the most beautiful things humans have ever achieved. And I think that's what I wanted to say, what I've been circling around this whole time. Mathematics isn't just a tool, isn't just a language, though it's both of those things. It's a window into the structure of reality, a way of seeing the patterns that underlie everything, a connection between the abstract and the concrete, between thought and existence, between the map and the territory. And the more we explore mathematics, the more we find that it's not just us imposing patterns on a chaotic world, but us discovering patterns that were already there, patterns that are fundamental, that make the universe what it is. And that's astonishing, that's profound, that's the kind of thing that makes you stop and wonder, makes you realize how strange and beautiful existence is, how remarkable it is that anything exists at all, let alone that it exists in a way we can understand, in a way that speaks to us in the language of mathematics. And maybe we'll never fully answer why that is, why mathematics works, why the universe is comprehensible. But the asking itself, the wondering, the endless curiosity that drives us to explore these questions, that's part of what makes us human, and it's part of what connects us to the mathematical structure of the cosmos, to the deep patterns that make existence possible. Now, let's move on to another theory for you to reflect on. I've been thinking a lot about energy lately, and it's one of those things that we use the word all the time, right? We say we're low on energy, we talk about energy drinks, energy bills, renewable energy, the energy of a room. It's everywhere in our language. But when you actually stop and think about what energy is, when you really dig into it, it becomes this strange, almost mystical concept that sits at the very heart of how the universe works. And here's the thing, here's what makes it so profound. Energy never dies. Never. Not once, not ever, in the entire history of the universe. Every bit of energy that existed at the moment of the Big Bang is still here, still around, still doing something. It just changes form. It transforms. It moves from one state to another, one configuration to another, but it never, ever disappears. And that fact changes everything about how we understand reality, how we understand ourselves, how we understand what it means to exist at all. Think about it this way. Right now, as you're reading this or listening to this, energy is flowing through your brain. Electrical signals, chemical reactions, heat. That energy came from the food you ate, which got its energy from the sun through photosynthesis, or from animals that ate plants that got their energy from the sun. The sun got its energy from nuclear fusion, from the conversion of mass into energy, from the gravitational collapse of a cloud of hydrogen and helium that formed billions of years ago. And that matter, that hydrogen and helium, that came from the Big Bang itself. So in a very real sense, the energy powering your thoughts right now is the same energy that's been around since the beginning of time. It's just been on a journey, a long, winding, complicated journey through stars and space and planets and life, and now you. And when you're done thinking these thoughts, that energy won't disappear. It'll become heat. It'll radiate out into the room, into the walls, into the air. It'll keep moving, keep transforming, keep existing forever. But let's back up a bit, because to really understand how strange and beautiful this is, we need to understand what energy actually is, and that's not as straightforward as you might think. You see, energy is one of those fundamental concepts in physics that's almost impossible to define in simple terms. It's not a substance, not a thing you can hold or see or touch. It's more like a property of the universe, a way of keeping track of something that's conserved, something that stays constant, even as everything else changes. The physicist Richard Feynman once said that we have no real understanding of what energy is. We just know how to calculate it, how to track it as it moves from place to place and form to form. And that's actually pretty profound. We've built all of modern physics, all of modern technology, all of our understanding of the universe on this concept that we can't really define except to say that it's the thing that's conserved, the thing that doesn't change in total amount. The story of how we discovered this, how we came to understand that energy is conserved, that's a fascinating journey through the history of science. It starts in a way with steam engines. That might seem like an odd place to start when we're talking about one of the deepest truths of the universe, but that's how science often works, right? We start with practical problems, with trying to build better machines, and we end up discovering fundamental laws of nature. In the early 1800s, engineers were building steam engines, trying to make them more efficient, trying to get more work out of them for less fuel. And in studying these engines, scientists like Sadi Carnot started to understand something about heat and work, about how you could convert one into the other. They realized there were limits, fundamental limits to how efficient you could make an engine, and those limits were telling us something deep about the nature of energy itself. But it wasn't just about steam engines. Around the same time, in the 1840s, a whole bunch of scientists in different places, working on different problems, started to converge on this same idea that energy is conserved. There was Julius Robert von Meyer, a German physician who was working on a ship in the tropics, and noticed that the blood of sailors looked different in warm climates. That observation, strange as it sounds, led him to think about heat and energy, and eventually to formulate the principle of conservation of energy. There was James Prescott Joule in England, doing careful experiments with falling weights and spinning paddles in water, measuring exactly how much mechanical work it took to raise the temperature of water by a certain amount. He was showing that heat and work were the same thing, just different forms of the same underlying quantity. And there was Hermann von Helmholtz in Germany, approaching it from a more theoretical perspective, showing that if you added up all the different forms of energy in a system, kinetic and potential and heat and chemical, the total stayed constant. And what's remarkable is that they were all finding the same thing, this same fundamental principle, from completely different directions. It was like explorers approaching a mountain from different sides and all arriving at the same peak. And what they found was something that seemed almost magical at first. Energy in all its forms is conserved. You can't create it, you can't destroy it, you can only transform it from one type to another. And that principle, that law, it's called the first law of thermodynamics now, and it's one of the most fundamental laws in all of physics. It applies everywhere, at all times, in all situations. From the smallest quantum interactions to the largest movements of galaxies, energy is always conserved. But here's where it gets interesting, and this is something that took me a long time to really wrap my head around. When we say energy is conserved, we're not just saying that the total amount stays the same. We're saying something deeper. We're saying that there's a fundamental symmetry in the laws of physics, a kind of mathematical beauty that means energy can't just appear or disappear. The physicist Emmy Noether proved this in 1915 with what's now called Noether's theorem. She showed that every conservation law, every quantity that stays constant in physics, corresponds to a symmetry. The conservation of energy corresponds to the fact that the laws of physics don't change with time. Today, yesterday, tomorrow, a billion years from now, the same laws apply. And because of that symmetry, because of that time independence of the laws of physics, energy must be conserved. It's not just an empirical observation, it's a deep mathematical necessity arising from the structure of reality itself. So what does this actually mean in practice? What does it mean to say that energy never dies, that it just transforms? Well, let's think about it in terms of everyday experience, because that's where it becomes real, where it becomes something more than just an abstract principle. When you eat breakfast in the morning, you're taking in chemical energy stored in the molecular bonds of your food. That energy gets broken down in your body through metabolism, through this incredibly complex series of chemical reactions. Some of it gets converted into ATP, adenosine triphosphate, which is like the energy currency of your cells. Some of it becomes heat immediately, which is why your body stays warm. The ATP gets used by your muscles to move, by your brain to think, by all your organs to function. And every one of those processes converts energy from one form to another. The chemical energy becomes kinetic energy, becomes electrical energy in your nerves, becomes more heat. And that heat radiates out from your body, warming the air around you, spreading out into the environment. But it doesn't stop there. The warmth that radiates from your body heats up the air molecules nearby. Those air molecules move faster, they have more kinetic energy. They collide with other molecules, spreading that energy around. Some of that energy might rise as convection currents. Some might be conducted through walls or floors. Eventually, some of it radiates out into space as infrared radiation, as heat radiation that travels at the speed of light out into the cosmos. And even then, even as that radiation spreads out, getting more and more diffuse, more and more spread out, it's still energy. It's still there. It might warm a speck of dust in space. It might eventually be absorbed by some distant object billions of light years away, but it never disappears. It's still part of the total energy budget of the universe. And this happens with everything, with every process. When you turn on a light bulb, electrical energy flows through the filament or through the semiconductor in an LED, and it gets converted into light and heat. The light photons travel out, they bounce off walls and objects, they get absorbed and re-emitted, they eventually get converted back into heat. When a tree grows, it's capturing light energy from the sun through photosynthesis and storing it as chemical energy in its wood and leaves. When that tree dies and decays or burns in a fire, that stored chemical energy gets released again as heat and light. When you drive a car, the chemical energy in gasoline gets converted into kinetic energy of motion and heat through the engine. The kinetic energy moves you from place to place, but it also gets dissipated through friction with the road and air resistance converted back into heat. Always heat, eventually. That's a pattern we'll come back to. But let's think bigger for a moment. Let's think about where all this energy came from in the first place. Because if energy is conserved, if it never dies and never gets created, then where did it come from? And this is where things get really strange and profound. The energy in the universe, all of it, seems to have come from the Big Bang. I say seems to because it's more complicated than that, but let's start there. At the moment of the Big Bang, about 13.8 billion years ago, the universe was incredibly hot and dense, and it contained all the energy that exists today. But here's the weird thing. Before the Big Bang, or at the moment of the Big Bang, we don't really know how to apply the concept of energy conservation because time itself was just beginning. The laws of physics, as we understand them, break down at that singularity, at that moment of infinite density and temperature. But after that first moment, once time started flowing and space started expanding, energy conservation kicked in. And all that energy, all that primordial heat started transforming. In the first moments, it was pure radiation, photons of incredible energy. As the universe expanded and cooled, some of that energy got converted into matter, into particles. This is one of the most beautiful things about physics. Matter and energy are actually the same thing. Einstein showed us that with E equals mc squared, that famous equation. Energy can become matter. Matter can become energy. They're interconvertible. So in the early universe, energy became quarks and electrons, and those quarks combined to form protons and neutrons, and those combined to form the first atomic nuclei. And through all of this, the total amount of energy, if you count the mass energy of the particles, plus the kinetic energy of their motion, plus the energy in the radiation, stayed constant. And then, as the universe continued to expand and cool, something else happened. Gravity started pulling matter together. Clouds of hydrogen and helium started to collapse under their own weight. And when they collapsed, gravitational potential energy got converted into kinetic energy. The particles moved faster and faster as they fell inward, and that kinetic energy got converted into heat through collisions. And eventually, in the centers of these collapsing clouds, it got hot enough and dense enough for nuclear fusion to begin. Hydrogen atoms were crushed together so hard that they fused into helium, and in that process, a tiny amount of mass got converted into a huge amount of energy, according to E equals mc squared. And that energy poured out as light and heat, and the first stars were born. And those stars, those beautiful burning spheres of plasma, they're energy transformation machines. They take the mass energy locked up in hydrogen and convert it into light and heat and kinetic energy and the mass energy of heavier elements. Our sun, the sun that's keeping us alive right now, converts about 4 million tons of mass into energy every single second. That's how much mass gets converted into pure energy through fusion in the sun's core every second. And that energy radiates outward, takes about 1 million years to work its way from the core to the surface, bouncing around, being absorbed and re-emitted countless times, and then it streams out into space as light. And 8 minutes later, some of that light reaches Earth. It warms our planet, it drives our weather, it powers photosynthesis, it makes life possible. And eventually, after doing all that work, it radiates back out into space as heat. But it's still there, still energy, still conserved. Now you might be thinking, okay, so energy is conserved, it transforms but never disappears. But doesn't that seem kind of obvious? I mean, we know that stuff doesn't just vanish, right? But here's the thing, here's where it gets subtle and profound. Even though the total amount of energy stays the same, even though it's conserved, not all forms of energy are equal. Some forms are more useful than others. And this is where the second law of thermodynamics comes in, and this is where things get really interesting, and honestly, kind of unsettling. Because while energy never dies, it does become less useful. It spreads out, it dissipates, it becomes more evenly distributed, and in doing so, it becomes harder to harness, harder to use to do work. This is the concept of entropy, and it's one of the most important and profound concepts in all of science. Entropy is often described as disorder or randomness, and while that's not a perfect description, it gives you a sense of it. The second law of thermodynamics says that in any closed system, entropy always increases over time. Things become more disordered, more spread out, more evenly distributed, and what this means for energy is that while the total amount stays the same, it tends to flow from concentrated forms to diffuse forms, from ordered forms to disordered forms. Heat flows from hot objects to cold objects, never the other way around spontaneously. Concentrated chemical energy in a log gets converted into diffuse heat energy when the log burns. The useful concentrated energy becomes less useful, more spread out energy, and this is happening everywhere all the time. It's the reason why perpetual motion machines are impossible, why you can't build an engine that's 100% efficient, why you can't get more energy out of a system than you put in, and why you can't even break even, as the old joke goes. Every time energy transforms from one form to another, some of it becomes heat, and that heat spreads out into the environment. And once energy becomes heat at the temperature of the surrounding environment, it's very hard to extract work from it. It's still there, it's still energy, but it's no longer in a useful form. It's like having $1 million in pennies scattered across an entire continent. The money is still there, the total amount hasn't changed, but good luck collecting it all to buy something. So in a sense, while energy never dies, it does age. It becomes less potent, less concentrated, less able to cause change and do work. And this has profound implications for the fate of the universe. If entropy is always increasing, if useful energy is always becoming less useful heat, then what's the ultimate end state? What happens when all the energy in the universe is evenly spread out, when everything is the same temperature, when there are no more differences in energy concentration to drive processes? This is called the heat death of the universe, and it's one of the possible far future scenarios that physicists talk about. Not death in the sense that the energy disappears, but death in the sense that nothing can happen anymore. No change, no processes, no life, just a vast, cold, dark, uniform sea of incredibly diffuse energy spread across an unimaginably enormous space. But we're getting ahead of ourselves. Let's pull back and think more carefully about what energy actually is, because we've been talking about it transforming and being conserved. But what is this thing that's being conserved? And this is where things get philosophically interesting, because energy isn't really a thing at all, not in the way we usually think about things. It's more like a property, an abstract quantity that we calculate. When you have a ball sitting on a shelf, we say it has gravitational potential energy. But it's not like the ball contains some glowing substance called energy. The potential energy is really just a mathematical way of keeping track of the fact that the ball could fall, that there's a configuration of the system that would lead to motion. And when the ball falls, that potential energy gets converted into kinetic energy, into the energy of motion. But again, the kinetic energy isn't some substance inside the moving ball. It's just a way of describing the fact that the ball is moving and has momentum and could do work if it hit something. The physicist and philosopher Bertrand Russell once pointed out that we don't really know what energy is intrinsically. We only know its mathematical properties, its relationships, how it behaves. We know that it's conserved. We know the equations that describe how it transforms. We know how to measure it in different forms. But what it actually is, in some deep ontological sense, that's mysterious. It's like knowing the rules of a game perfectly without knowing what the game pieces are made of. And maybe that's okay. Maybe that's all we need to know. But it does make you think about the nature of reality, doesn't it? If one of the most fundamental things in the universe is something we can't really define except through its properties and relationships, what does that say about the nature of existence? And there's another layer to this, another way in which energy is stranger than it first appears. In quantum mechanics, energy becomes even more abstract and bizarre. At the quantum level, energy is quantized. It comes in discrete packets called quanta. Light energy comes in packets called photons. The energy levels in an atom are discrete. Electrons can only have certain specific energies, not any value in between. And energy and time are related through Heisenberg's uncertainty principle in a weird way. The more precisely you try to measure when something happens, the less precisely you can know its energy, and vice versa. And there's this thing called vacuum energy or zero-point energy, where even empty space, even a perfect vacuum, has energy. The quantum fields that permeate all of space are constantly fluctuating, constantly creating and annihilating virtual particles. And this gives space itself an inherent energy, even in the absence of any matter or radiation. And then there's the whole question of how energy relates to the fabric of space-time itself. Einstein's general theory of relativity tells us that mass and energy curve space-time, they bend it, and that curvature is what we experience as gravity. So energy doesn't just move through space, it actually shapes the geometry of space itself. A massive star distorts space-time around it, and that distortion is felt as gravity. Light follows curved paths near massive objects, not because the light is being pulled by a force, but because space-time itself is curved, and the light is just following the straightest possible path through that curved space. And this means that energy is intimately connected to the structure of the universe itself, to the very framework in which things happen. But let's bring this back to something more immediate, more personal. Let's think about life, about living things, because life is fundamentally about energy. Life is a process, a flow of energy through matter. We often think of living things as objects, as things that exist, but really we're more like patterns, like processes, like whirlpools in a river. The water in a whirlpool is constantly changing, always flowing through, but the pattern, the whirlpool itself, maintains its structure. And that's what life is like. The atoms in your body, they're constantly being replaced. The food you eat becomes part of you. The atoms get incorporated into your cells, and other atoms get expelled. Over the course of about 7 years, most of the atoms in your body get replaced, but you persist. the pattern persists, because there's a constant flow of energy maintaining that pattern, maintaining that structure. And that flow of energy, that's what life is. We take in low entropy energy, concentrated energy in the form of food, or if you're a plant, in the form of sunlight. We use that energy to maintain our structure, to move, to grow, to think, to reproduce. And we release high entropy energy, dissipated energy, back into the environment as heat and waste products. We're entropy decreasing machines locally, creating order within our bodies, but we can only do that by increasing entropy elsewhere, by taking in ordered energy and releasing disordered energy. We're like little islands of decreasing entropy in a sea of increasing entropy, and we can only maintain ourselves by accelerating the increase of entropy around us. And this gives you a different way of thinking about death, doesn't it? When a person dies, when any living thing dies, the energy doesn't disappear. The atoms that make up the body are still there. The energy that was flowing through those atoms is still there. What stops is the process, the pattern, the organized flow of energy that maintained the structure. The energy that was bound up in the chemical bonds of the body's molecules gets released. If the body decays, bacteria and fungi break down those molecules and use the chemical energy for their own processes. If the body is burned, the chemical energy is released rapidly as heat and light. But the energy persists, it just flows in new directions, takes new forms. The atoms return to the earth or the air or the water. They become part of other things, other processes. The carbon in your body might become part of a plant, or dissolve in the ocean, or float in the atmosphere as carbon dioxide. The energy that animated you disperses, spreads out, joins the great flow of energy through the biosphere and beyond. And in that sense, we're all connected through energy. The energy in your body has been part of countless other things before you. It's been part of plants and animals and bacteria. It's flowed through the oceans and the atmosphere. It's been in rocks and soil. Before that, it was in the food that other creatures ate. Before that, it came from the sun through photosynthesis, or from the earth through geothermal processes, or from the chemical energy stored in the earth from ancient life forms now fossilized as coal and oil. And before that, it came from the sun, which got it from fusion, which got it from the gravitational energy of the collapsing gas cloud, which got it from the Big Bang. And after you, after your life, that energy will continue flowing. It'll be part of other life forms, other processes. It'll heat the air and the earth. Some of it will eventually radiate into space as heat, but it won't die. It can't die. There's something profound and maybe even comforting about that, I think. We are temporary patterns in an eternal flow of energy. Our bodies, our thoughts, our experiences, they arise from this flow and return to it. We're like waves on the ocean. Each wave is distinct, has its own character, its own moment of existence, but it's made of water that was part of other waves before and will be part of other waves after. The wave dissipates, breaks on the shore, or merges back into the sea, but the water persists. And we're like that with energy. We're temporary configurations of matter maintained by a flow of energy, and when that particular configuration ceases, when that pattern breaks down, the energy flows on. It doesn't mourn us, it doesn't remember us, but it continues, eternal and unchanging in total amount, ever-changing in form. And this connects to some really deep questions about identity and persistence and what it means to exist. If the atoms in your body are constantly being replaced, if the energy flowing through you is always changing, then what are you really? What persists? Is it the pattern? Is it the information encoded in your neural connections? Is it something else entirely? These are questions that philosophy and neuroscience and physics are all grappling with in different ways. But what's clear is that we're not static objects. We're processes, dynamic systems maintained far from equilibrium by a constant influx of energy. And that process, that pattern, is what we call life, what we call consciousness, what we call ourselves. Now let's think about this on a larger scale. Let's think about the energy flows that govern our planet, our solar system, our galaxy, the universe. Earth is an open system. It receives energy from the sun and radiates energy back into space. If those two flows were exactly balanced, Earth's temperature would stay constant. but they're not always exactly balanced, and that's partly why we have climate change. We're putting more greenhouse gases into the atmosphere, and those gases trap some of the outgoing infrared radiation, preventing some of the energy from escaping as quickly. So the energy input from the sun stays the same, but the energy output decreases, and the difference accumulates as increased temperature. The energy is still conserved, but the distribution changes, the balance shifts, and that has profound consequences for life on Earth. And the sun itself, our ultimate source of energy for almost everything on Earth, it's slowly using up its fuel. The hydrogen in its core is being converted into helium through fusion, and that process releases energy. But there's only so much hydrogen. Eventually, in about 5 billion years, the sun will run out of hydrogen in its core. Then it'll start fusing helium into heavier elements, and it'll expand into a red giant, engulfing the inner planets, possibly including Earth. And eventually, it'll shed its outer layers and become a white dwarf, a small, dense, hot ember, slowly cooling over trillions of years. But even then, even as the sun dies, the energy doesn't disappear. The energy released during its lifetime has radiated out into space at the speed of light. Some of it warmed Earth and made life possible. Some of it flew off into the cosmos. The energy locked up in the heavy elements created in its core will be released when those atoms are eventually incorporated into other stars or planets. The heat of the white dwarf will slowly radiate away into space over unimaginable timescales. But it's all still there, all still energy, all still conserved. And this is happening with every star in the universe. There are hundreds of billions of stars in our galaxy and hundreds of billions of galaxies in the observable universe. Each star is a furnace, converting mass into energy through fusion, pouring light and heat out into space. And all of that energy, all of it, is the same energy that's been around since the Big Bang. It's just cycling through different forms, different configurations. Some of it gets locked up in planets and moons and asteroids. Some of it becomes black holes, where it gets trapped by such intense gravity that not even light can escape. But even there, even in black holes, the energy isn't destroyed. It's just sequestered, held in a place where it can't affect the outside universe, at least not until the black hole eventually evaporates through Hawking radiation, which is a whole other mind-bending aspect of this story. Stephen Hawking showed, using quantum mechanics and general relativity, that black holes aren't actually completely black. They emit radiation very slowly due to quantum effects near the event horizon. Virtual particle pairs pop into existence right at the edge of the black hole, and sometimes one particle falls in while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. And as it emits this radiation, it loses mass, it loses energy, it slowly evaporates. For a stellar mass black hole, this process takes an absurdly long time, far longer than the current age of the universe. But given enough time, trillions upon trillions upon trillions of years, even black holes evaporate completely. And when they do, the energy that was trapped inside gets released back into the universe as radiation. Again, conservation of energy. The energy was sequestered, hidden away, but not destroyed. Eventually, it comes back out. So if we follow this logic, if we trace the energy flows to their ultimate conclusion, what does the far future of the universe look like? This depends on the exact properties of the universe, on things like dark energy and the rate of expansion, which we're still trying to understand. But in many scenarios, the universe continues to expand forever, and as it expands, it gets colder and more diffuse. Stars eventually burn out. New stars stop forming because all the gas gets used up or spread too thin. Galaxies drift apart, separated by ever-increasing distances. Black holes evaporate. And eventually, in the unimaginably distant future, 1 to the power of 100 years from now or more, we reach something called the heat death or big freeze. The universe becomes a vast, cold, dark expanse filled with nothing but incredibly diffuse radiation, photons stretched out to absurdly long wavelengths, moving through a space that's barely above absolute zero in temperature. And at that point, there's essentially no usable energy left. Oh, the energy is still there, every bit of it that ever existed. But it's so spread out, so evenly distributed, that nothing can happen anymore. No stars, no planets, no life, no change, just stillness, eternal, cold stillness. And that's a bit depressing, isn't it, to think that the ultimate fate of everything might be this slow dissipation into nothingness. or not nothingness exactly, but into a state where nothing interesting can ever happen again. But there are a few things to keep in mind. First, this is so far in the future that it's almost meaningless to us. We're talking about timescales that are billions of billions of billions of times longer than the current age of the universe. Second, we don't actually know for certain that this is what will happen. There could be processes we don't understand yet, aspects of physics we haven't discovered that change the picture. Maybe the universe will collapse back on itself in a big crunch. Maybe dark energy will behave differently than we expect. Maybe there are quantum effects that become important on cosmological scales at late times. We simply don't know. And third, even if this is the ultimate fate, it doesn't diminish the reality and meaning of what happens before then, of what's happening now. The energy flowing through the universe right now, creating stars and planets and life and thought, that's real and beautiful and meaningful, regardless of what happens trillions of years from now. But let's come back to something I mentioned earlier, E equals mc squared, because this is one of the most important pieces of this puzzle and one of the most beautiful connections in all of physics. Energy and mass are equivalent. They're two sides of the same coin. Mass is really just an incredibly concentrated form of energy. When you hold a rock in your hand, you're holding a tremendous amount of energy. If you could convert all the mass in that rock into energy, if you could annihilate it completely with antimatter or something, the amount of energy released would be staggering. A 1 kilogram rock contains about 90 quadrillion joules of energy, which is enough to power a city for months. We don't normally notice this because mass is so stable, it doesn't just convert into energy spontaneously, but the energy is there, locked up in the mass itself. And this equivalence between mass and energy, it's one of the most profound insights of special relativity. Einstein showed that mass and energy are related by this simple equation, E equals mc squared, where c is the speed of light. And because the speed of light is such a large number, about 300 million meters per second, and because it's squared in the equation, a tiny amount of mass corresponds to a huge amount of energy. This is why nuclear reactions, both fission and fusion, release so much energy. In these reactions, a small amount of mass gets converted into energy, and that energy is enormous. When uranium splits in a fission reaction, about 0.1% of its mass gets converted into energy. When hydrogen fuses into helium in the sun, about 0.7% of the mass gets converted. These seem like small percentages, but because of that c-squared factor, they result in tremendous amounts of energy. And this means that when we talk about energy conservation, we really need to include mass. The full conservation law is actually conservation of mass energy. In any process, the total mass energy, the sum of the mass and the energy, stays constant. Most of the time, in everyday situations, mass and energy can be treated separately because the conversions between them are negligible. But in high-energy processes, in particle accelerators, in stars, in the early universe, you can't ignore the conversion. Matter can be created from energy and energy from matter, but the total amount of mass energy is always conserved. And this has some really interesting implications for the nature of matter itself. What we think of as solid matter, the stable stuff that makes up our bodies and the earth and everything around us, is really just a stable form of energy. The atoms in your body, the protons and neutrons in those atoms, they're made of quarks held together by gluons. And the mass of the proton doesn't even come mostly from the mass of the quarks. It comes from the energy of the gluon fields, from the kinetic energy of the quarks zipping around inside the proton, from the binding energy of the strong force holding it all together. When you add up all these contributions, you get the mass of the proton. So in a very real sense, mass is energy, just energy in a particular configuration, energy bound up in matter. And here's another strange thing. When you climb a mountain, you gain gravitational potential energy. Your mass energy increases slightly. And that increase has to come from somewhere, because energy is conserved. Where does it come from? It comes from the system doing the work, from your muscles, from the chemical energy you're expending to climb. But here's the weird part. You actually get slightly more massive as you climb. Not much, an absurdly tiny amount, far too small to measure with any scale. But in principle, according to relativity, your mass increases because you have more energy. Similarly, when you heat something up, it gets more massive. A hot cup of coffee is very, very slightly more massive than a cold cup of coffee because it contains more thermal energy. Again, the difference is unmeasurably small in practice, but it's real in principle. This blurring of the distinction between matter and energy, between stuff and the ability to do work, it's one of the most profound shifts in how we understand the physical world. In the classical Newtonian view, matter and energy were separate things. Matter was the stuff, the tangible objects, and energy was this abstract property they could have. But in the relativistic view, they're united. Matter is energy, energy is matter, and what persists, what's conserved, is the totality of both. And when we say energy never dies, we're really saying that this total, this mass energy never dies. It can shift from one form to the other, from matter to radiation and back again, but the total remains constant. Now, I want to spend a moment on the arrow of time because it's intimately connected to energy and entropy, and the idea that energy, while conserved, becomes less useful over time. The arrow of time, this is the concept that time has a direction, that the future is different from the past in a fundamental way. We remember the past but not the future. We see causes leading to effects, not effects leading to causes. Eggs break but don't spontaneously unbreak. And all of this is tied to the second law of thermodynamics, to the increase of entropy. In the microscopic laws of physics, at the level of individual particles, time is reversible. If you filmed particles interacting and played the film backward, the backward version would still obey the laws of physics. But at the macroscopic level, the level of everyday experience, time clearly has a direction. And that direction is set by entropy. Entropy increases over time in a closed system, and that increase defines the arrow of time. The future is the direction in which entropy is higher. The past is the direction in which entropy was lower, and this is why we see the processes we do. Heat flows from hot to cold because that increases entropy. Perfume diffuses through a room because that increases entropy. Living things age and eventually die because the organization and low entropy of a living system requires constant energy input to maintain. And without that input, entropy increases and the organization breaks down. And energy is at the heart of this. Energy naturally flows from concentrated forms to diffuse forms because that's the direction that increases entropy. When you burn a log, you're converting the concentrated chemical energy in the wood into heat and light that spread out into the environment. The total energy is the same, but the entropy has increased dramatically. The organized molecules of the wood have been converted into disorganized gas molecules and photons and heat. And this process is irreversible in practice. You'll never see the smoke and ashes spontaneously reassemble into a log and suck heat out of the environment to do so. Not because it's impossible in principle, but because it's so absurdly unlikely that it effectively never happens. The entropy of the log is lower than the entropy of the smoke and ashes, and processes spontaneously go from low entropy to high entropy, not the other way around. So the arrow of time, our sense that time flows in one direction, is really tied to the fact that energy naturally dissipates, naturally spreads out. And this is why we can't build a perpetual motion machine, why we can't extract unlimited energy from the environment. If we could somehow reverse entropy, we could also reverse time in a sense. We could unbreak eggs, unmix colors, reassemble broken things. But we can't. Energy is conserved, but it's also degraded. It goes from useful to less useful, from concentrated to diffuse, from organized to disorganized. And that degradation, that dissipation, that is the arrow of time. There's something poetic about this, I think. The universe is a one-way street, at least at the level of entropy. We're all moving forward together from the low entropy state of the Big Bang toward higher and higher entropy states. Energy flows through us, through everything, maintaining temporary islands of order, temporary decreases in local entropy, but always at the cost of increasing entropy elsewhere. And eventually the energy becomes so spread out, so diffuse, that no more work can be done, no more interesting processes can happen. The universe reaches its maximum entropy state, and time, in a sense, ceases to have meaning because nothing changes anymore. But we're not there yet, not by an inconceivably long shot. Right now, we're in what you might call the interesting era of the universe. Stars are burning, planets are forming, life is arising and evolving, complex structures are being created and destroyed, energy is flowing, transforming, doing work, creating beauty and complexity and thought. And all of this is possible because the universe is still far from equilibrium, still has gradients and differences that energy can flow across. The sun is hot, space is cold, and that difference, that gradient, that's what powers life on Earth. And similar gradients exist throughout the universe, powering all the processes we see. Let me take a different angle on this. Think about it from the perspective of information, because there's a deep connection between energy, entropy, and information that's only been fully appreciated in recent decades. In the 1940s, Claude Shannon developed information theory, which is a mathematical framework for understanding communication and information. And it turns out that the concept of entropy in information theory is closely related to entropy in thermodynamics. Both are measures of uncertainty, of the number of possible states a system could be in. And in the 1960s and 70s, physicists like Rolf Landauer and Charles Bennett showed that information is physical, that erasing information requires dissipating energy, increasing entropy. Every time a computer erases a bit of information, it has to release a certain minimum amount of heat into the environment. This is called the Landauer limit, and it's a fundamental connection between information processing and thermodynamics. And this connects to the idea that energy transformations are really about information transformations. When energy goes from a concentrated form to a diffuse form, when entropy increases, what's really happening is that information is being lost. The concentrated energy state contains more information, more structure, more order. When it becomes diffuse heat, that information is lost, dispersed into the microscopic random motions of countless particles. And we can't recover it, can't put it back together without expending more energy elsewhere, increasing entropy somewhere else. So in a very real sense, the life of the universe is the story of information being gradually erased, of structure being gradually dissolved, of order becoming disorder. But not uniformly, not everywhere at once. Locally, temporarily, structures can arise. Complexity can increase. Life can evolve. Thought can emerge. All of this is possible because there's still usable energy, still gradients to drive processes, still differences to exploit. But every time complexity increases somewhere, entropy increases more somewhere else. Every time information is created in one place, more information is destroyed elsewhere. The overall trend is always toward dissipation, toward uniformity, toward heat death. And yet, even knowing this, even understanding that we're all part of this irreversible flow toward higher entropy, there's still something beautiful about it. We exist because of this flow, our complexity, our consciousness, our ability to think and feel and wonder. It all arises from energy flowing through matter, creating temporary structures of incredible intricacy. We are the universe becoming aware of itself, to use Carl Sagan's phrase. We're arrangements of atoms that can contemplate the laws that govern those atoms, and that's possible because energy is flowing through us, maintaining our structure, powering our brains, enabling our thoughts. And when we die, when that flow stops, the energy doesn't disappear. It returns to the environment. The atoms of our bodies become part of the earth, the air, the water. They might become part of plants, animals, other people. The energy that animated us disperses, radiates away as heat, but it's still there. And in that sense, we never truly leave. We're transformed, dispersed, but not destroyed. We're returned to the elements, to the flow of energy through the cosmos that has been going on since the beginning of time and will continue until the end, if there is an end. There's a Buddhist concept, I think, about how nothing has independent existence, how everything is interdependent, connected to everything else. And in a physical sense, that's true. The energy in you came from countless other things and will go to countless other things. The atoms in your body have been recycled through stars and planets and living things for billions of years. You're not separate from the universe. You're a temporary pattern in the universe, a way that the universe has organized itself for a moment. And that pattern will dissolve, but the stuff of it, the matter and energy, that goes on. And maybe that's a more hopeful way to think about death, about endings, not as a stopping, not as nothingness, but as a transformation, a return to the flow. The energy that was you doesn't cease to exist. It can't. It's conserved by the fundamental laws of physics. It changes form, it disperses, it joins the vast circulation of energy through the cosmos. And some of that energy, somewhere, somewhen, will be part of something new, something that exists and experiences and maybe even thinks. The universe recycles everything. Nothing is wasted. Nothing is truly lost. Of course, the pattern that is you, your specific memories and personality and experiences, that's tied to the specific configuration of atoms in your brain, and that configuration doesn't persist. When you die, that information is lost, erased, dissipated into thermal noise. And that's the tragedy of death, really. Not that the energy disappears, but that the pattern, the information, the unique perspective that was you, that comes to an end. But even then, the effects you had, the things you did and said and created, those ripple outward. They affect other people, other systems, other patterns. In that sense, your influence persists even after you're gone. The energy may disperse, the pattern may dissolve, but the consequences of that pattern having existed, those continue to propagate. And thinking about this, thinking about energy conservation and entropy and the flow of information, it gives you a different perspective on what matters, on what's important. We're here for such a brief time, such an infinitesimally small fraction of cosmic time. And while we're here, energy is flowing through us, enabling us to act, to create, to connect with others. How we direct that energy, what patterns we create with it, what effects we have, that's our choice to some degree. We can't stop the flow, can't halt the increase of entropy, can't prevent our own eventual dissolution, but we can choose what we do with the energy while it's flowing through us. We can create beauty or ugliness, connection or isolation, understanding or ignorance, joy or suffering. And those choices matter, even if only temporarily, even if only locally. Let me circle back to something I touched on earlier but want to explore more deeply. The idea of energy at the quantum level, because this adds yet another layer of strangeness to the whole picture. In quantum mechanics, energy isn't just conserved in a classical sense. It's quantized, meaning it comes in discrete units, and it has this weird relationship with time through the uncertainty principle. The Heisenberg uncertainty principle says that you can't know both the energy of a system and when that energy state occurred with perfect precision. The more accurately you know one, the less accurately you can know the other. And this leads to some really strange phenomena. For instance, quantum mechanics allows for brief violations of energy conservation over very short timescales. Virtual particles can pop into existence out of nothing, borrowing energy from the vacuum, as long as they disappear quickly enough that the borrowed energy times the time they exist is less than Planck's constant divided by 4 pi. These are called vacuum fluctuations, and they're happening everywhere, all the time, throughout all of space. Particle-antiparticle pairs spontaneously appear and annihilate, borrowing energy from nothing and returning it before the universe notices, so to speak. And these aren't just theoretical curiosities. They have real, measurable effects. They contribute to the Casimir effect, where two metal plates placed very close together in a vacuum experience a tiny attractive force. They affect the energy levels of atoms, causing tiny shifts in spectral lines that we can measure with incredible precision. So energy is conserved on average over long enough timescales, but at the quantum level, over extremely short timescales, it can fluctuate. The universe is, in a sense, constantly borrowing energy from the future and paying it back or borrowing from the past in these incredibly brief quantum events. And this is all consistent with energy conservation in the long run, but it shows that energy at the quantum level is even stranger and more subtle than we might have thought. And then there's the whole question of what energy means in the context of quantum field theory, which is the framework that combines quantum mechanics with special relativity. In this picture, what we think of as particles are really excitations of underlying quantum fields that permeate all of space. An electron is an excitation of the electron field, a photon is an excitation of the electromagnetic field, and so on. And energy is a property of these field excitations. When you have a photon traveling through space, you have energy and momentum carried by an excitation of the electromagnetic field. When the photon gets absorbed by an atom, that energy goes into exciting the electron to a higher energy level, which is a different configuration of the electron field. The energy is transferred from one field excitation to another, but it's conserved throughout. And in this framework, even empty space, even the vacuum, is filled with these quantum fields in their ground state. And the ground state, the lowest energy state, still has energy. This is the vacuum energy I mentioned earlier, the 0-point energy. Even if you could remove every particle, every bit of radiation from a region of space, it would still have this inherent quantum vacuum energy. And this energy, it might be related to dark energy, the mysterious energy that seems to be causing the expansion of the universe to accelerate. We don't fully understand dark energy yet, but one possibility is that it's the energy of empty space itself, the quantum vacuum energy. If that's true, then the acceleration of the universe's expansion is being driven by the energy of nothing, by the inherent energy of the vacuum. And this raises profound questions. If the vacuum has energy, where did that energy come from? Has it always been there? Is it part of the initial energy budget of the universe from the Big Bang? Or is it something else? We don't really know. And the amount of vacuum energy we calculate from quantum field theory is absurdly larger than what we observe, by something like 120 orders of magnitude, which is one of the largest discrepancies between theory and observation in all of physics. Something is clearly wrong with our understanding, but we don't know what. Maybe the vacuum energy is much smaller than we calculate for reasons we don't understand. Maybe it's cancelled out by something. Maybe our theories are incomplete. This is one of the biggest unsolved problems in theoretical physics. But whatever the resolution, whatever the true nature of vacuum energy, the principle remains. Energy is conserved. The total energy of the universe, including the energy of the vacuum, including the energy of matter and radiation and dark matter and dark energy, all of it adds up to some total that doesn't change over time. It might transform, fields might change, particles might be created and destroyed, but the total energy, the sum of everything, that stays constant. At least that's what all our observations and theories suggest. In a universe that's expanding, in curved space-time, the definition of total energy becomes tricky and subtle, but locally, in small enough regions of space-time, energy is definitely conserved. And that's enough to say that energy, in its essence, is eternal. There's one more aspect I want to explore, and that's the practical side of this, the engineering and technological side. Because understanding energy conservation, understanding how energy transforms, is the basis of all technology. Every machine, every device, every tool we've ever created works by harnessing energy transformations. A steam engine converts heat into mechanical work. An electric motor converts electrical energy into kinetic energy. A solar panel converts light into electricity. A battery stores chemical energy and releases it as electrical energy. All of these are examples of energy being transformed from one form to another, and the efficiency of these transformations is limited by the laws of thermodynamics. And this is where entropy comes in again. The second law tells us that no energy transformation can be perfectly efficient. Some energy always gets converted into waste heat, into random thermal motion that we can't easily harness. The best heat engines operating between a hot reservoir and a cold reservoir are limited by the Carnot efficiency, which depends on the temperatures of the two reservoirs. The closer those temperatures are, the lower the efficiency. And this is why power plants, whether they run on coal or natural gas or nuclear energy, are only about 30 to 40% efficient at converting heat into electricity. The rest of the energy gets released as waste heat, warming up rivers or the atmosphere. But here's the thing. Even though that waste heat is wasted from the perspective of doing useful work, it's not destroyed. It's still energy. It's still part of the total energy budget. It's just dispersed, spread out into the environment in a form that's harder to use. And this is true of every energy transformation everywhere. Inefficiency doesn't mean energy is lost. It means energy is converted into less useful forms. When you drive a car, only about 20 to 30% of the chemical energy in the gasoline actually goes into moving the car forward. The rest becomes heat in the engine, heat from friction, sound, vibrations. But all of that is still energy. It just isn't doing what you want it to do. And this has huge implications for things like climate change and energy policy. When we burn fossil fuels, We're converting chemical energy that was stored millions of years ago, energy that came from sunlight captured by ancient plants and plankton, into heat and motion and electricity. But ultimately, most of it becomes waste heat. And that waste heat accumulates in the atmosphere and oceans, warming the planet. The energy doesn't disappear, it stays in the Earth system, and it changes the climate. Addressing climate change is really about managing energy flows, about changing how we harness energy and where that energy ends up. And as we look to the future, as we think about sustainable energy and renewable resources, we're really thinking about how to tap into energy flows that are already happening, rather than releasing stored energy from the past. Solar energy taps into the constant flow of energy from the sun to Earth. Wind energy taps into the kinetic energy of air masses set in motion by uneven heating of the planet. Hydroelectric power taps into the gravitational potential energy of water that was lifted up by evaporation powered by the sun. Geothermal energy taps into the heat of the Earth's interior, which comes from radioactive decay and leftover heat from the planet's formation. All of these are ways of harnessing energy that's already flowing, already in motion, without releasing additional stored energy. And the beautiful thing is that the energy from these renewable sources is constantly being replenished. The sun keeps shining, keeps pouring energy onto Earth. The Earth's interior keeps generating heat. As long as these processes continue, as long as energy keeps flowing, we can tap into those flows. And eventually, yes, the sun will die, the Earth will cool, but that's billions of years away. For now, for the foreseeable future of human civilization, we have access to more energy than we could possibly use if we can figure out how to harness it efficiently. And efficiency, improving efficiency, that's really about reducing the amount of energy that gets converted into waste heat, about keeping energy in more useful forms for longer. Better insulation means less heat leaking out of buildings, which means less energy needed for heating and cooling. More efficient engines mean more of the fuel's energy goes into useful work and less into waste heat. Better batteries mean less energy lost in charging and discharging cycles. All of these improvements don't change the total amount of energy, they don't violate conservation, but they do change how much useful work we can extract before the energy dissipates into unusable heat. And in a way, this is what life does too, right? Life is incredibly efficient at capturing and using energy. Photosynthesis in plants converts sunlight into chemical energy with remarkable efficiency, sometimes up to 6% for the whole plant, much higher for just the initial light reactions. Cellular respiration in our bodies converts chemical energy into ATP with efficiencies around 40 to 60%, depending on the molecule being metabolized. These are impressively efficient processes, honed by billions of years of evolution, and they have to be efficient because life is competing for limited energy resources. The organisms that can capture and use energy more efficiently have an advantage. They can survive and reproduce better. So in a sense, the history of life on Earth is a history of evolving better and better ways to harness energy flows, to maintain complex organization far from equilibrium, to decrease local entropy at the expense of increasing it elsewhere. And we humans, with our technology, have become extraordinarily good at this. We've learned to tap into fossil fuels, into nuclear energy, into renewable flows. We've built machines that can convert energy from one form to another with reasonable efficiency. We've created a global civilization that runs on vast flows of energy, transforming resources and moving goods and information around the world. And all of this is possible because energy is conserved, because we can predict how it will transform, because the laws of thermodynamics are reliable and universal. But we're also seeing the limits of this. We're seeing that the waste heat and waste products from our energy use are changing the planet's climate, altering ecosystems, causing extinctions. We're realizing that we need to be more careful about how we manage these energy flows, about where we get our energy and what we do with the waste. Because while energy is conserved, the distribution of energy matters enormously for life and civilization. Too much waste heat in the wrong places can be catastrophic. And this brings me back to something fundamental. Energy conservation is a law of nature. It's not something we can change or violate. But how we direct energy flows, how we use energy, that's a choice. We can choose to burn fossil fuels and release stored carbon into the atmosphere, or we can choose to harness solar and wind and other renewable flows. We can choose to waste energy through inefficiency, or we can choose to improve our technologies and reduce waste. The total energy is conserved either way, but the consequences for us and for the planet are vastly different. And I think understanding this, really deeply understanding energy conservation and entropy and how energy flows and transforms, it changes how you see the world. You start to see everything as processes, as flows, as transformations. A city is a massive energy metabolism, taking in fuel and electricity and food, converting it all into motion and light and heat and waste. A forest is a solar collector, capturing sunlight and storing it as biomass, cycling energy through countless organisms. Your body is an engine, burning fuel, maintaining organization, radiating heat. Everything is energy in motion, energy transforming, energy flowing from concentrated forms to diffuse forms, creating temporary structures along the way, structures that exist only because energy is flowing through them. And when those flows stop, when the energy source is cut off, the structures decay, entropy increases, organization breaks down. But the energy persists. It flows elsewhere, takes new forms, powers new processes. The cycle continues, the great circulation of energy through the universe, from the Big Bang to the heat death, if that's indeed the fate that awaits. And we're part of that cycle, insignificant in the vast scale of cosmic time and space, but significant in this moment, in this place where energy is flowing through us and enabling us to wonder, to question, to understand. You know, there's something deeply humbling and deeply empowering about this knowledge. Humbling because it shows us that we're not separate from nature, not exempt from physical law, not permanent. We're temporary patterns maintained by energy flow. And when that flow stops, we dissolve back into the undifferentiated matter and energy of the universe. But empowering because it shows us that we're connected to everything, that the energy in us is the same energy that powers stars and shapes galaxies, that we're made of the stuff of the cosmos and subject to the same eternal laws. And for a brief moment, that energy has taken a form that can think and feel and love and create. That's remarkable, that's precious, that's worth celebrating, even knowing it's temporary. And maybe that's the ultimate lesson here. Energy never dies, but forms do. Patterns emerge and dissolve. We can cling to the illusion of permanence, or we can accept the reality of transformation. We can fear death, the dissolution of the pattern that is us, or we can find comfort in knowing that the energy, the fundamental stuff of our existence goes on, not as us, not with our memories or personalities or identities, but as something, as part of the ongoing dance of energy through matter, the endless transformation that is the universe. And in our brief time, while the pattern persists, while energy flows through us, we have the opportunity to be aware, to understand, to appreciate the strangeness and beauty of existence. We can look at the stars and know that we're made of the same atoms, powered by the same energy. We can hold another person's hand and feel the warmth of energy flowing, the heat of metabolic processes, the miracle of organized complexity maintained by a constant influx of energy. We can create art, music, literature, science, technology. All of these are ways of organizing energy and matter into meaningful patterns. Patterns that can affect others, that can propagate through culture and time. And when we're gone, when our individual patterns dissolve, those effects remain, at least for a while. The ideas we shared, the things we created, the people we touched, those ripple outward. They're not eternal. Nothing is eternal except energy itself, but they persist longer than we do. And in that sense, we transcend our brief existence, not through the persistence of our individual consciousness, but through the persistence of our effects, our influences, our contributions to the great ongoing experiment that is life and consciousness and civilization. So energy never dies. It's eternal, unchanging in quantity, ever-changing in form. It flows from the beginning of time, if there was a beginning, to the end, if there will be an end. And we're part of that flow, brief eddies in the current, temporary patterns in an eternal transformation. And that's enough. That has to be enough, because it's the truth, the deep physical truth about the nature of existence. Energy is conserved. Energy is eternal. Energy never dies. And for a moment, just a moment in cosmic time, some of that energy is you, is me, is all of us, thinking and feeling and wondering about itself. And then it flows on to whatever comes next, forever and ever, without end,